I'll briefly recap convolutional neural networks. I have floated several slides on advances in deep learning, basically training algorithms, as well as different approaches to regularization, decreasing the bias, increasing the variance and so on. Obviously we do not have time to cover everything. So we will cover convolutional neural networks, and then I would like to cover recurrent neural networks, but that would require a little bit also background of graphical models, and I will cover graphical models as foundation and also touch upon Bayesian networks. That will be the flow. Obviously we will not be able to do everything today. This will be the flow for the next one or two classes. So recap that we discussed some Lego blocks in modern deep learning. I mean, these are really Lego blocks. Lot more has happened ever since they came up. We talked about the depth feature map, the red, green and blue channel, and in general it's good to keep in mind this view. So especially when we talk about everything until pooling, here's the input image and the input image comes with RGB. And then this could be say 128 by 128. There is an effect of funneling down by virtue of application of these different patches, of a patch along with strides and so on. But in that process, what you typically do is increase the depth. This is the depth. So the depth typically increases. Say 20 or something like that. Now, in this process, we have also shrunk the length and the width. Now, what is exactly happening is that the patch that is moving around, thanks to striding and something we discussed called pooling today, they lead to shrinking in this sense. But the depth often increases because we do not apply a single convolutional filter, you apply multiple filters. Okay, so the increase in depth is largely due to application of multiple filters. So for example, we talked about the Sobel filter, but Sobel is an edge detector, vertical edge detector, horizontal edge detector. Now we are not going to force the kind of filter, we are going to learn those filters, but in the process of learning we do not expect one filter to serve all purposes. So we let the network learn different filters. All filters are learned, okay, or by training. Okay, so it's good to keep this in mind. And finally, after some more processing, what you will get, these are different colors, what you will get is softmax. I mean, ultimately you will do softmax. Say softmax over 10 or whatever, 10 classes. For example, the 10 digits, the softmax over 10 classes. The intermediate layers have learned how to detect edges, how to detect different components of 6 and 0 and these different digits. And they are trying to learn this in a way that's agnostic to the RGB representation. I give you a 1 in green and a 2 in blue. I should be able to generalize my classification across these different colored inputs. So good to keep this in mind. And specifically two that enable downsampling, two components here. So one is the striding enables downsampling, and the other is pooling. We have not yet discussed this. We will discuss today. Now, what were each of these doing? What was patch in conjunction? Patch was basically what? Local connections. And it's good to keep this example in mind. I am trying to learn how to detect a car. The patch that moves around tries to consider local connections and detect local objects, and I already gave example of edges, right? So this is a case of patch. And strides they enable downsampling, and basically you are saying that the patch will skip pixels at regular frequency. Okay, that's what stride is about. So you are saying that this patch would probably move in these small units and so on. Padding was largely to do with the corners, and we talked about zeroed padding, valid padding. So when this filter moves into a corner, what should you do? So padding says that for example, zero padding. Corners, edges. Now even after this, we may want to do something more, and that is pooling. But let's quickly recap what each of this was doing. So I showed this in a one-dimensional case, and then on the text we generalize it to multiple dimensions. So patch idea is sparse interactions, neighboring signals are always more relevant than ones that are further away. That is the first patch, local connections. And therefore you started indexing weights not using x comma y, but using say x minus y, in this case I minus m, that was the index, right. So this was the patch I minus m. Now not only did we apply this index for local connections, but we also thought we can share parameters, and the weights also got indexed by these differences, which means these weights we started sharing those weights. So in fact local connections and shared weights, the same patch is moving around. So this corresponds to moving patches around the image. And then we talked about striding and padding. So stride corresponds to moving the patch. As I said, it is some kind of sampling, and at the corners you do padding, and then we give example of these filters, blurring filters, sharpening filters. Obviously we want to be able to learn these filters and not just force these filters. Then we, towards the end of last class, we talked about the size. What would the shrinking down effect be? So let's say my original image had dimensions m cross n. That was my original image dimension. My patch had dimension p cross q. And let's say I was doing some padding here. Okay, so padding, extra padding. Let's say padding was 0 padding of size d. Then we were trying to, yeah, and one more. What is missing here? There's something missing here. Size of the image, huh? Patch should have up. Okay, so good point. So this patch, we are actually talking about this patch in the XY plane. So maybe I should show it differently. So this is the patch. P, Q. Now this patch also has a depth. Depth is typically going to be just the depth we have here. So depth is not really important here because we are just going to sum across the entire thing. Whatever is the depth here, we are going to, there is no sampling in the depth, there is no striding or sampling, you are not moving vertically. We still have missed out one thing. We talked of patch size, we talked of padding. What about stride? The downsampling effect. So the stride size, how much you move this unit at a time is S. Okay. So this stride size S, patch size P cross Q, and padding, let's say 0 padding of size D. Can the stride be different for the x and y axis? You can make it different. We will keep it the same. You can make it S subscript M and S subscript N. So in this case, for example, the stride, the patch is moving 1 pixel at a time. The stride size is exactly 1. And you are padded with size 4, S equals 4 non-zero, and you keep doing this till the filter hits the right hand bottom corner. What is the resultant size here? What is the dimension here? So we can basically move this by how many units? So there is a there's a D here, there's a D here. So M plus 2D, N plus 2D, right? So that can be one thing. M plus 2D something something cross N plus 2D something something. And I know roughly that I need to divide by S because I am going to not take move across every pixel, I am going to jump pixels. So you are saying we also need to subtract the length or the width of the filter itself, right? I mean I have kind of padded, but then obviously I can't make this left end move to the the right end move beyond the pad. The padding is so that I can restrict myself, right? You can't have padding on padding. So padding you can't overflow that, which means you could have just gone all the way until here. So that will be n plus 2d minus p n plus 2d minus Q divided by S. Have we missed out something? Whole thing plus 1. Why are we talking about plus 1? Because the place where you started. Yeah, I mean the offset from where you began needs to be added plus 1. So you can look at all these in action here: sparse interactions, parameter sharing, and equivalent representation, equivariant. All these are in place. And equivariant, I want to remind you that equivariant is not invariant. I think there was a safe quiz problem, right? Invariance versus equivariance. So equivariance would mean that f gx is the same as g fx. It's not that f is not effective at all. It's just the order I am able to change. But when I say something is rotation invariant, what do you understand by rotation invariance? Invariance. Whether I rotate or not, sorry, property will they say the same. For example, density, right? If I wanted like mass by volume of an object in 3D. Now rotate the object, does the density change? It doesn't change, right? So there are many properties which are invariant to certain transformations, but this is not invariance. I mean, you have to apply the transformation. So it's f of g of x is g of f of x. Here I again remind you what our example of f and g were. F was example the filter operation, filter addition, adding all the elements within the filter, and G was shift. So you do the filter and then shift, or shift and then filter, we will get the same result. And now we just trying to apply these m plus 2d minus p divided by s plus 1 and try and estimate what the output size will be, right, and compare that with what you would get with a CNN, with a normal neural net, fully connected neural network. So fully connected neural network gave you 4.8 billion parameters, and that was with 40,000 neurons, hidden layer. Now let's quickly see if CNN has 20 feature maps. So here said depth is 20. Depth is 20 means 20 feature maps. This is also called feature maps. Number of feature maps. So if depth is 20 and 5 by 5 by 3, right? So we are saying that m equals n is 200, n is 200, now RGB is 3 obviously, and then 20 feature maps. Initial depth was 3, then it became 20, and P equals 5, Q equals 5. Okay, so now I want you to quickly figure out and compare. Figure out what this size will be. You have pretty much everything you require on the board. So any answers? Yes. Anyone? Sorry? Plus bias. Okay. Let's ignore bias for the time being. 1500 weights. How did you get 1500? Exactly this. No. This is the number of, what is this? This is the outputs. This is the number of neurons into the depth, obviously. Right? This is the number of neurons. So, what is the weights correspond to? Filters. And how many filters are we talking about? Okay, 20 into 20 into P into Q, right? That's all we are talking about. 20. Pardon? For each input channel, you have you mean RGB? No. So this P into Q into 3, the whole thing into 20. So yeah, you're right. So P into Q into 3. This is RGB input channels into 20 depth. Okay, what we are saying is for each layer in the depth, we have a different filter operational. $1,500, and how does that compare with 4.8? I mean 4.8 now you realize is meaningless for a nicely structured problem like this. Yeah, you could just have a bias at the end. I mean, let's just assume that bias is also kind of given as an input. Basically, it's modeled through a dummy one input, right? You can just give some dummy layer, dummy column in the input. Okay, so his point is if you do that, that hack won't fit with our convolution. You're right. Or I mean, you might do a convolution, it will just give a little bit of noise that will introduce. For the time being, we are ignoring bias. You can accommodate it at the end, post facto. How many neurons? So you realize that strides is not affecting the number of parameters, it's only affecting the number of neurons. So how many? Anyone? Into? So something like this. Yeah, 204 and 200, 420. And so it's around 8,32,000. That's the order. Okay. So as you can see, the number of parameters is much less than 4.8 billion. And this number of output is a bit larger than 40k, right? This 40k is what we had earlier. So in comparison, we have more outputs, pure inputs, but then outputs are now meant to represent some aspects of the input. So we are not necessarily sad about it because they are going to make some sense. Parameters is what we are a little bothered about. Now somebody may say, okay, what about subsequent processing? I mean, this layer will land up having to deal with lot many more neurons. But remember, we are again going to use convolution. We may use convolution there as well. We may, I am not saying we will, but if we use convolutions there, again we will have much fewer parameters. And then I also pointed out that if D equals P minus 1 divided by 2 and S equals 1, what do you get? Output size will become equal to input size. Okay, now people, I mean now you can, creative brains can be put to work. People have also thought of deconvolution. Again, this is really optional, but I just wanted to tickle your imagination. So what would you do in deconvolution if you were allowed to? What would you do? Convolution says I am going to apply filter, summarize information. Deconvolution would try and desummarize. Okay, so I coined a new word deconvolution. He coined a new word desummarize. Right? So expand, elaborate. So let's say I want to elaborate image from compressed features. That's exactly what deconvolution does. So something like this. So from small you get to the bigger. Again, I have no discussion on this, just to give you an idea that these things happen. Now the deconvolution is often used, say I want an input image to be summarized. Remember PCA? Right? What did PCA do? So I tried to find principal components so that it explains the data. So deconvolution is often used in conjunction with convolution to get a PCA like effect. So from here, let's say you go here, basically do this and come back. Con plus decon gives you PCA like effect. Okay, so this is really a part of also unsupervised learning. I mean, if you were to put together convolution plus followed by deconvolution. So PCA, please understand that though it goes, I mean it's rooted in stuff that was done way back, PCA has really resurfaced in a lot of deep learning, the same concept of PCA. Just that PCA had a nice mathematical characterization. Many of these cases you will have to kind of force some kind of decorrelation between the different components. Right? I mean the components in PCA, I gave you two interpretations. There was some orthogonality that you may have to force here. It is not there by design. So now I will get to one more additional component that is used. So far the stride was serving a purpose that I really don't have to go through every pixel, I mean shift the patch through every pixel. What is often done is, well, you may not even require, even after the output, you may not require all these neuron values. Somebody may say 8323200 has become really much larger than 40K. Can I make it comparable? 40K was what you got with a fully connected network, fully connected layer. So to solve this, you can do further downsampling. Could also downsample the output neurons. Okay, but this downsampling will be slightly different. So think of I mean let's say I look at all these neuron outputs here, right? Which would you pick? Would you just again pick at random intervals? Now this is a lot more than just it's not just about structure, it is also getting you some signal whether the edge was there or not, whether vertical edge was there, whether the horizontal edge was there. So how would you downsample? If I were to pick some, if I allowed you to pick some of the neuron activations here, which neurons would you pick? One with larger values. I hope it's not coming from a previous reading of this subject. Now one with larger values is what one of your friends says, and that's what people thought early on, but now people have started questioning whether larger is really the right thing. Whether one size fits all, should it be larger in every situation? But the point is that some specific patterns in the output is what you should capture. And one of the first ideas that was thought about, the pooling idea, was based on max. It's also a filter. It's called the max pooling filter, and as your friend pointed out, I'll just pick some of the maximum activations in this amongst these neurons. So max based sampling, pick the max value, it's called the max pooling filter, okay, for every chunk. Now again you'll have to, the max pooling filter will also have a size, say think of, let me actually do this here, let me apply the max pooling filter here, in a particular patch. So I'll have this as again some P times Q max pooling. So what it's going to do is, in this patch is going to say, well, this is the max value, let me pick this. It'll again move the patch and pick a max value in the next section. Keep doing this. So all the previous parameters, size P, size Q, strides, how much do I can stride there as well. So all those basically resurface. If you read a typical paper on CNN, read a set of papers on CNN, convolution sometimes is thought of as all of these together. You can think of the affine transformation, that's what I talked about earlier. The first filter, addition filter, where you just basically sum across all the points in that. This is what we have discussed, and then you may do some rectified linear unit, some activation, and then do a pooling. Okay, so this pooling I am talking about is often thought of as part of the convolution itself. That is the complex layer terminology. Often people think of this as one convolution block, but some other papers say no, convolution is only this, pooling is separate from that. Okay, so mind the language of the paper, so understand where pooling, what constitutes convolution, is pooling part of convolution or not. Okay, so the max pooling filter, now I call this a non-linear filter and non-linear downsampling filter because it's really looking at some max value. It could have been also min value instead of max value. So it's a sample based discretization process. One of the objectives is diamond standard reduction. Again I bring to your attention, I said 8,32,000, that's I've increased the dimension overall across all the layers in the depth, right. So I might want to shrink the dimension, that's the motivation, and this is translation invariant. This is interesting. This also affects, let's say I'm trying to detect an anomaly, a mass space, let's say. So somebody is having a mass space, and let's say my model was to detect people with mass spaces. Now the guy with the mass space might be hiding in different regions of this image. Okay, so and mask may correspond to some peaking of some signals, right. So max is generally because we are interested in some phenomenon. Okay. So when we say max based signaling, sampling, some signal that peaks. So for example, if I am detecting mass space, it's a signal that peaks, and with respect to that object, detection of that object, it's translation invariant. So my object could have been here, now it has moved somewhere else, or I mean locally translation, I mean not completely different place, but some local translation, max is basically going to capture that. That's another interesting property. and obviously we know dimensionality reduction also helps you avoid overfitting. So these are some interesting properties. So yes, an example in 1D, input is 4, 5, 6, 7, 8, and let's say I apply a max pooling filter, P equals 3, M equals 5, this is one dimensional, there is no Q, there is no N, and the output is 6, right, the max value between 4, 5 and 6. And I'll shift to the right using a stride of 1, I get 7. Hope you are able to see the translation invariance aspect here. Okay, so I would say a little bit of local here, it's local translation invariance. So which means that if I had moved the 6 to 4 and 4 to swap the positions, I would have got the same value in that local segment. Okay, and so on. So this is using stride of 1. Now what if the stride changes to 2, what will be the output? The stride were 2, what would you get? You should get 6 and 8, right? 6 and 8. Okay, so you will get 6 and 8. So the more the stride, the more aggressive the downsampling or dimensionality reduction. So you can work out the output size. Typically in max pooling there is no sense doing padding. Okay, so it has all the elements except padding. No padding. So these are all characteristics. So because of that, the 2D disappears, everything else remains the same. M minus P divided by S plus 1 is the size of the output, and N minus Q divided by S plus 1 is the output. Okay, so you can look at the JavaScript again. So I mean, you can now start seeing all these different elements in action. So digit classification, let's say I look at that. I mean, yeah, the CFAR 10, that's probably more interesting. Let's look at that. You can set your learning rate and so on, and then start. You can these different examples are being provided for training, and you can see the activation gradients. Now this is a convolutional layer, 32 by 32. That's the size of the P is 32, Q is 32. 16 is the depth on which it's operating. Okay, and activation gradients and weights. Then you have done a ReLU immediately after that, and then there's a max pool. The max pool is just finding the max value. Pooling size is 2 by 2, so it's going to kind of reduce the dimensionality by 2. This is a pool, and it's trying to find the activations. It's just trying to find where the activation peaks in those different blocks. So you can see that there is a sharpening effect that the pooling operation is bringing in. So only getting the max value. Now you may not want the sharpening effect. In fact, you may want, let's say someone is trying to hide an object, it's an anomalous activity. You may want a min instead of max, or you may want average. Okay, but here we are looking at sharpening things, so it's max. And yeah, again another convolution after that has been applied here, and again a ReLU, again a pool, again convolution, and you can see there are couple of those. Finally there's a softmax, and you can look at predictions. Things are getting, some of them are getting classified correctly, bunch of mistakes, but the training accuracy would probably increase as iterations proceed. The tutorial, we have couple of 2 or 3 problems which are just about documenting your observations, and yeah, you'll also look at what happens if you, in each of these networks, if you change the ReLU with a tan H, what difference would you expect? So all of this is for you to think. Problem 5, in the answer is a little bit more detailed. So most of the other problems in the tutorial 7 are have to do with derivations. These 2 problems are mostly observational. So AlexNet is one of the earliest architectures, 2012, which made use of this really complex machinery, building blocks, build on complex machinery based on the building blocks. The first convolutional layer took an input of size 224 by 3, right, and then there were 48 features, 48 was the depth, and the stride was 4, and then there was a max pooling which kind of shrunk, which did the nonlinear downsampling, reduced the size to 55 by 55 for each layer. So it's a max pooling using a 3 by 3 filter. Okay. So, and the last layers are all fully connected. Now it's not that every layer has to have convolution. You could also have fully connected. You may want to start looking at interactions between the different activations that you have learned using convolution. Okay, so this is interesting that some of the last layers may just be fully connected. These are dense layers, and often they model interactions between objects. Okay. So there's one more Lego block I want to do. I won't be doing in such great details. That's called the RNN. Inception, I have kind of left it as optional reading. Inception builds on CNNs and multiple basically filters, lots of filters. RNN and LSTM, they deal with structure and output. So let's say I'm trying to not just predict the class label for an image, but I'm trying to generate a caption for an image. Okay, so let's say I give you this image, car image. You can do captioning whatever so you can use CNN whatever you want to model the input. But let's say my task was slightly different than just classification. So let's say the task was ingest this big model and produce a caption. So what would be a caption for this image? Bad car. For some reason he didn't like it. Okay. Old car. Standing under a tree which is about to fall. Okay, let's say the tree has branches coming all the way here. Obviously there will be some occlusions. So now the target is to produce a sequence of words as an output, right? So this requires you to model dependencies in the prediction. I mean, it doesn't make sense to say old car standing under a car or standing under a man. Obviously it has to be standing under something which is larger. So the general properties of words you produce need to have some common sense adherence to what we call a language model. Okay. So RNNs come to a rescue there. Now I want to give you a little hint on like logistic regression. People have you've studied logistic regression. One of the simplest extensions to logistic regression that gave you a mechanism to be able to produce a sequence as output was a conditional random field. So this is trying to building on logistic regression. This is just one slide. So in the case of logistic regression, you had only y1, x1, right? But suppose I had x1 and let's say x1 is today, x1, x2 are day of week, and y1, y2 are say temperature. Okay. And we can go back to our captioning example also, but let's say it's a simpler example, day of week and temperature. So what logistic regression says is, well, I look at the day of the week, the properties of today, features of today, and try and predict the temperature. The features could be humidity level, right, day of the week, month of the week, 1 month of the year, and so on. But then you know that there is often some pattern to the temperature. It is not that today is say 32 and tomorrow the max temperature becomes 45. You don't expect that. So there is some structure to the output. I mean similar to the structure here I said, but this structure requires little bit more work to understand why 3 should follow A, which should follow under, which should follow standing, right. This is easier to understand. So y1 is temperature today, y2 is temperature tomorrow and so on, and expect temperatures to follow a pattern. Either gradually increasing, gradually decreasing, so some kind of smooth pattern. And one way you try and bring in that smoothness is by adding potentials or adding these features also across the outputs. So y1 should not be too different from y2, right. So can you think of something that binds y1 to y2? So done logistic enough, right. So what would this form look like? Any suggestion? The simplest is that y1 is close in magnitude to y2. How do you put that using some function? Distance function, okay. What we would often do is exponentiate it. So distance function is a suggestion, but you would exponentiate it so that we can use probability models. So one form is e raised to minus norm of y1 minus y2 square, something like this. And then as we discuss a little bit on graphical models, we will see why all this makes sense. So this is basically a simplest extension to logistic regression in the form of something called the conditional random field. Okay, so I want you to do the following, everyone. So I want you to recap the logistic regression distribution, probability of y, and now tell me how you would extend that for something called conditional random field. Everyone, please. So all of you might recall what the form of the logistic probability distribution is. Probability of y given a class, right, and let us say temperature is also discrete classes, only 5 temperatures, high, very high, high, medium, low and very low. Let us say there are 5 temperatures possible, okay. So you have probability of y is one of these two, right, y element of very high, high, medium, low, very low, given x, y1 given x1. This is what you have had in the past. Now what would this due distribution look like? Everyone should pay attention, and I would like you to try and write down. I mean it's okay if it's wrong, I want you to stretch your imagination. What would you do now to handle a slightly more tricky case when there is structure in the output? The outputs D2 follow some smoothness. There are multiple inputs. When we looked at the likelihood function earlier, what is the assumption we made on the likelihood? What is the assumption we made while computing the likelihood? Probability of y1 comma y2. Your quiz 2 last week. Yes? Independence. So we said that yi's are independent of each other given the xi's. Do you have that anymore? No, okay. So what we are looking at is probability of y1, y2, yn given x1, x2, xn, and this is no longer equal to product over i's of probability of yi given xn. If it is no longer equal to this, then tell me what you could do. So give me an expression, give me some, it's okay if it's not normalized, a proper normalized probability distribution. I mean, this is one form. So his question is, should we be using distances? I'm saying it's not necessarily distances. I mean, distance is when I assume y1, y2 to be some actual temperature value. But if it's just high, very low, you may do it differently. I mean, you can also use, let's say I map very high to 5, high to 4, and I can do that also. So I can have an indicator function associated with each of those classes. So, I mean, you can come up with any function that is reasonable. It could be y1 minus y2, but through a mapping. So, this propose something. If the question isn't clear, let me know. I am looking for an alternative. So, I don't want this assumption to kill me. I have nicely captured the car image, nicely captured the input, but my output cannot be arbitrary. My output needs to have some structure. In the case of a car caption, I need the words to follow some meaningful pattern. In the case of temperatures, I want tomorrow's temperatures to be reasonable given the prediction of today's temperature. They are related to each other, they are not independent given the inputs. So, can you help me fill up some possibility here? I just want you to think wild. Wild in an ML AI manner, so within the boundaries of probability, try to make it look like a valid probability distribution. Okay, good question, so good suggestion. Instead of assuming that y1 is independent of all the other yi's given xi, I will say, well, y1 is independent of y3 given y2, or y2 is independent of, y3 is independent of y2 given y1. So, they are still making an independence assumption, but it does not ignore the structure on the output altogether. Okay. So, the suggestion is probability of y1 comma y2 comma y3 given x1 comma x2 comma x3. So, something like this. I don't have to always use probability here. So, I will just say it's proportional to some function exp of, I will just make it this exp of some potential function phi which involves y1, y2 given the x1, x2. In fact, I am going to do this for all pairs yi, yj, xi, xj. So, if let us say I and j are neighbors, I have just taken your Q and generalized it. I said it is a product across these pairs y1, y2, x1, x2, some potential of that, phi is, I am generalizing from features to potentials. Okay. So, I say phi is some function of not just the input but also the output, and that phi internally could be using distance between phi y1, y2, whatever, but this is a form. Now, I mean, I spoke slightly different from what, sorry, your name, Saksham. So, Saksham said slightly different from what I said. I said I am going to now create small groups and create potentials on them. What Saksham said was the output y1 is independent of y3 given y2. Okay, so let me write that form as well. So what he said is, if y1 is conditioned on y2, y3 and x1 to xn, I could just drop y3 of the conditioning. In general, what he is saying is, if yi and yj are neighbors, all I need to know is yj and the xis. Alternately, you could also limit the xis, that's also a possibility. I don't need to look at all the xis. I'll say, well, I'm going to also drop anything other than x1, x2 say. Okay, so this is very interesting that we have come up with two different characterizations. One is in terms of independence, it's called conditional independence. The other is in terms of factorization, right? And this is a subject, one important subject of graphical models. Graphical models give you two different views into this world. One is in terms of independence and the other is in terms of the specification of the distribution through factorization. This is the independence view and this is the factorization view. So I am going to switch to probabilistic graphical models for maybe a class or two, and that will be also related to your next tutorial plus lab. So what are probabilistic graphical models? They are graphical representations of probability distribution. I give you some probability distribution. How do I represent this? So graph gives you one way of looking at this distribution, and we'll be giving very simple examples, and I'll revisit this captioning kind of problem once we have delved a bit into graphical models. They've been, when they were developed, they started helping you abstract what you already knew, right? New insights into existing model, but that also gave rise to new models. And eventually, because you have graphs, you could think about flows on graphs. You could compute max weighted trees. Have you done weighted trees? Right. So algorithms that have been developed for trees, for graphs could be reused. And they really come at the intersection of probability theory and graph theory. So what are the components of a graphical model? You have a node which represents a random variable. Each of these y1, y2, yn will represent a random variable. In fact, even x1 into xn represent random variables. And there are edges between nodes. We saw a simple graph x1, y1, y2 and yn were all connected to each other, but not directly. Each yi was influenced by an xi. And there are edges between nodes. But very interesting, what is informative is not the edges, it is the absence of edges. Okay, so I really like to stress this point. These edges are informative because of the absence of certain edges, which means the degenerate case is when I add all edges. If every node is connected to every other node, there is no information. Basically, you are saying everything depends on everything. Right? How do I crack JE? So you need to have a good balanced diet, you need to keep good health, you need to wake up early, but then there's no kind of leading information on how you could really prepare for JE. So it's really meaningless. Everything is useful for JE, but there are certain things that are more important, right? So the graph is the absence of edges, saying that certain random variables don't depend on certain other random variables in some structured manner. That's what is communicated, the absence of certain edges, and we'll see many more examples. So information provided by presence of edges is in some sense vacuous. Vacuous means it's meaningless, it's redundant, and therefore the most useless information you can give me is saying x1 y1, x1 is also connected to y2, y2 is also connected to x2, x2 is also connected to y1, and so on. This is meaningless, not informative. Now there are two broad categories of graphical models. One is called directed, the other is undirected, and we will take an example of each. So directed graphical models, the example we will take is the most popular example is Bayesian network. All edges are directed. Okay, so x1 goes to x2, from x2 you have x3. Now you are also allowed DAG structure. It has to be directed acyclic graph. So you can't have directed cycles, you can have undirected cycles, but all edges are directed. Have you done directed acyclic graphs? Yes. So Bayesian network is a directed acyclic graph. Undirected, this is directed acyclic graph. Undirected, this is an example. This building on logistic regression, we had something called conditional random field. I would say this is the most straightforward extension of logistic regression, and that is a example of an undirected graph. And then you also have chain graphs which have both directed and undirected edges. So I have very detailed notes on graphical models. I have already posted them on Moodle. I will be referring to them for 1 or 2 lectures. Now coming to very interesting discussion that we had. So Saksham had suggested one view which was based on independence, and that is one characterization of graphical models. This is called the Markov or conditional independent property. Okay, the temperature today doesn't depend on the temperature day after tomorrow, or temperature day after tomorrow doesn't depend on the temperature today if I knew the temperature tomorrow. So that it's a block, is blocking the information, is blocking the flow of information. Tomorrow's temperature blocks the flow of information from today unto day after tomorrow, right? On the other hand, another way of specifying directed graphical models or undirected graphical models for that matter is through what I specified. It's called the factorization property. Now what makes graphical model a very interesting discipline is some sort of equivalence between these two specifications. Okay. So in some sense these two are equivalent, and I will tell you under what conditions they are equivalent. In the sense, I give you a graph and I say this graph has been built to honor some conditional independence properties, and then by looking at the graph and the conditional independence assertions, you are able to come up with the factorization that will respect the conditional independence. So that is the equivalence we are talking about. Okay. Conditional independence is very easy to think of, right? I mean, today's temperature should or day after tomorrow's temperature should be independent of today's temperature given tomorrow's temperature. It's very easy to think of. Now what will be the exact probabilistic model that will respect my independence? That is what factorization is about. Is that clear, the larger picture? These are the two questions. Factorization is about how to factorize the joint distribution given the graph. Conditional independence is, can we determine the conditional independence given the nature of the graph? Now it turns out that for undirected graphs this is very easy. For directed graphs it's a little subtle, the conditional independence. Factorization, I will not get into the details of equivalence and in this course, but factorization you can take it from me based on some intuition that I might provide. Okay, so let us look at factorization to begin with. For directed graphs, the factorization is that, so let us say this is a directed graph. The factorization is the joint distribution of these nodes P, x1, x2, x3, x4, x5 will be such that the probability, all I have to look at is the probability of a node given its parents. Okay, so the way I write, this is directed. I am going to erase this part. For this graph, probability of x1, x2, x3, x4, x5 is a probability of x3 given its parent x2 into the probability of x4 given its parents x2 and x5, probability of x2 given, x4 given x2 and x5 into probability of x2 given x1 into probability of x5 given x1. That is how you specify joint distribution for directed graphs. Okay, so probability of a node xi given its parents, all the parents, we call them PA xi, that's all matters in a complex graph. Undirected graphs, you only consider cliques. C here stands for cliques. This is an undirected graph. What are the maximal cliques, the largest cliques here? There are pairs, right? So in this case, the probability of x1, y1, blah blah blah, xn, yn, the joint distribution is probability of x1 comma y1, probability of y1 comma y2, probability of x2 comma y2, probability of y2 comma y3, and so on. Just the cliques. These are the maximal cliques. Okay. So in the next class I will resume from this point. I will again do a little bit brush up. We will show how intuitively this factorization gives you conditional independence in each case in directed or undirected graph.